materials as well. So without any further ado, I will turn it over to Pete to lead the presentation.
All right, thanks, Kelly. Hello, everybody. I'm Pete Millett, a Senior Technical Marketing Engineer at MPS. In today's webinar, we're going to discuss how to drive the gates of power MOSFETs. I'm focusing on using MOSFETs to drive motors, but these principles also apply to other uses of power MOSFETs. I've been working with motor driver ICs for about 15 years, doing product definition and systems and applications engineering at MPS and at Texas Instruments. Before that, I worked for many years as a board-level hardware engineer. So here's the agenda. First, I'll talk a little bit about power MOSFETs, how they're made, and how they work. Then we'll discuss how to properly drive the MOSFET gate and how to control the switching times. I'll use some simulations to demonstrate things. We'll also talk a little bit about MOSFET power drive circuits like H-bridges as they relate to gate drive. I'm sure most of you are familiar with power MOSFETs. They've become probably the most common semiconductor device used to switch power. They're used extensively in power conversion circuits like voltage regulators. They're also used to drive loads, everything from lighting to electromechanical actuators like motors and solenoids. Power MOSFETs are available in many different sizes and types. Voltage rating extend from a few volts up to several thousand volts, and currents from a few milliamps to thousands of amps. Obviously, to support this range of applications, there's many different physical package sizes, but generally, all these parts work the same way. Power MOSFETs are generally three-terminal devices. Current flows between the drain and source terminals, and the flow of currents controlled by the gate terminal. MOSFETs come in two polarities, N-channel and P-channel. That's analogous to an NPN and PNP transistor. Although there are many other types of MOSFETs, today we're focusing on enhancement mode devices that are used for power control. Enhancement mode means that the parts are off, not conducting any current, when the gate's at 0 volts relative to the source. So how do we use a power MOSFET to drive power to a load? Well, sometimes a MOSFET's used alone to drive the load. Example of this might be a lamp driver. It drives current in one direction to turn the lamp on, and the lamp goes out when the MOSFET turns off. If you're driving an inductive load, current needs to continue flowing after you turn a MOSFET off. When the inductor or inductive load, like a motor, is driven to a positive voltage, current ramps up. Then when you switch the load to connect it to ground, the current ramps down. To do this, you can use a diode and a single MOSFET, but usually we use two MOSFETs connected together in a half bridge. To drive loads like DC motors, where we need to send current in either direction, and with a DC motor that changes the rotation direction, we use two of these, one on each side of the motor. That's a full bridge or just an H bridge. A half bridge can be constructed with an N-channel MOSFET on the low side and a P-channel MOSFET on the high side. In this arrangement, the gate of the high side is driven to the load supply voltage, which is Vin in this diagram, to turn the high side off. To turn it on, the voltage has to be lowered by Vg, which is the voltage needed to turn the MOSFET on. The low side, on the other hand, using an N-channel MOSFET, the gate's at 0 volts to turn off and a positive voltage, Vg again, to turn on. At low supply voltages, that is low enough to be within the relatively low maximum gate to source voltage limit, which is often 20 volts or so. This arrangement's really easy to use because you can just connect the two gates together and drive them between 0 volts and Vin. That's like a normal CMOS totem pole output. But if the supply voltage is higher than the gate source maximum rating, the drive circuitry gets a little more difficult because now you have to create a voltage that's Vg volts below the Vn supply. So another way to do this is to use two N-channel MOSFETs. It's actually a more common way to drive high power loads like motors. And it's largely because N-channel MOSFETs are significantly less expensive than similarly rated P-channel MOSFETs. To use an N-channel as the high side, though, you need to drive the gate above the supply voltage to turn it on, because the source terminal has to go all the way to Vin to turn on the load. There's a number of ways to generate that gate drive voltage that's above the supply. Most gate driver ICs take care of generating that for you. So before we talk about how to drive the gate, I think it's useful to understand a little bit about how a power MOSFET works. I'm not a silicon expert, but I'll try to explain a little bit about how things work. So here's a cross-section drawing showing a typical N-channel MOSFET construction. This is called a trench FET. There's lots of other topologies to build a FET, but they all work in a similar way. The gate terminal is made from a conductive material, metal or polysilicon, that's floating on an insulator, which is usually silicon dioxide. So other than the current to charge and discharge capacitances, and we'll talk a lot more about that later, there's no DC current flow into or out of the gate. Current's conducted from the drain terminal to the source terminal. The current flows through a narrow area called the channel. When the gate terminal is at the same voltage as the source terminal, the small area of P-type silicon prevents current from flowing between the N-type drain and source. When a positive voltage is applied to the gate relative to the source, a small N-type channel is created in the P body region near the gate, and it allows current to flow. So you can think of this as a voltage-controlled resistor. The resistance of the channel from drain to source is very high when the gate voltage is below the gate threshold, which is called VTH or VGSTH. As you increase the voltage applied to the gate above that threshold, the resistance of the channel starts to drop. This allows more and more current to flow between source and drain. Eventually, you reach a region where the drain to source behaves like a linear resistor. That's up here. In switching applications, like most power applications, we're mostly concerned with two states, fully off and fully on. So we focus on driving the gate terminal quickly from the cutoff region with no current flow and the linear region, which is fully turned on. However, there are some reasons why we might want to slow down that transition, and we'll talk a bit more about that later. So I mentioned before the gate terminal is insulated from the drain and source by a thin layer of oxide. But this insulation layer is very thin, especially between gate and source, generally less than a micron thick, measured in angstroms. That means there's considerable capacitance between the gate terminal and the source and the drain. It's key to understand these capacitances and how they affect the gate drive circuitry. In addition to those capacitances, there's also parasitic inductances and resistances in a power MOSFET. Other than the on resistance, which is called RDS on, the resistance between source and drain when the MOSFET's fully turned on, we usually don't have to worry about these in normal power electronic applications. Usually the parasitics on the PC board are more significant. Those parasitics can become a factor, though, in very high-speed operation. So we can model all these parasitic bits to better understand how they'll affect our circuit. This schematic shows a model of a power MOSFET. The most important ones to consider when we're trying to design a gate drive circuit are the capacitance from gate to source, which is CGS, and the capacitance from gate to drain, which is CGD. To turn the MOSFET on and off, we need to charge and discharge these capacitances. So on a power MOSFET datasheet, you'll usually find those capacitances that we just saw in the model specified. So they lump two together, so the important one designing the gate driver is CISS. That's the total input capacitance, which is the gate to source capacitance in parallel with the gate to drain capacitance. To turn the MOSFET on, you need to charge that CISS to a voltage that will turn the MOSFET fully turned on. So one thing to note, the gate to source threshold voltage, VGSTH, is the voltage where the MOSFET just starts to turn on. To turn it fully on, you need to go a significantly higher voltage. Usually that voltage is listed as a condition for the RDS on spec. We see here that RDS on is specified at 10 volts on the gate, which implies you need at least 10 volts to get to that resistance. Another datasheet spec you can use to design the gate drive is the total gate charge, or QG. QG is a charge in coulombs. Actually, it's usually in nanocoulombs. Nanocoulomb 6.28 times 10 to the 9th electrons, by the way. So note that the total gate charge is always specified at a given voltage. In this example, 10 volts again. You might remember a basic expression, Q equals CV, charge equals capacitance times voltage. So really, a charge at a specified voltage equates to a capacitance. So in this example, if we take the 188 nanocoulomb gate charge and divide by the specified 10 volts, we get 18.8 nanofarads. It's not exactly the same as the input capacitance specified on the datasheet, but for the purposes of designing a gate drive, it's close enough, so you can use either one. Often it's more convenient to use the gate charge because of another basic equation, I equals Q over T, where current equals charge divided by time. So if you know that you need to charge the gate in a certain amount of time, you can then calculate the current that you'll need to put into the gate. So in this example, if we want the MOSFET to be on in a microsecond, we need 188 nanocoulombs divided by 1 microsecond, or about 188 milliamps of current. These are approximations, by the way. Be careful here though, because you would need a constant 188 milliamps of current to get the gate, to go into the gate for the full 1 microsecond. So we're essentially charging a capacitor, and most gate drive circuits are not constant current sources. They're just resistive switches. So the current will start out high and then drop, like any other RC circuit. All right, so now I'm going to show some examples of driving the gate of a power MOSFET. For these examples, I'll be using an N-channel MOSFET. P-channel MOSFETs work the same way, but current flows the opposite direction. Source is positive, drain negative. To turn a P-channel MOSFET on, you need to make the gate more negative than the source. So this is a schematic of a simple gate drive circuit that I'll be using with simulations to illustrate some of the topics as we go along. Note that this is simple. There's no constant current sources or any other fancy stuff. The circuit uses a NPN-PNP bipolar totem pole to drive, provide a low source impedance to the gate. I'll put a resistor in series to control how fast the gate charges and discharges. V3 here is the gate drive voltage, which is set at 12 volts. R1 is a load on the drain of the MOSFET, just a resistive load here. And the supply voltage on top of that is V2. The MOSFET here is a typical modern high power MOSFET, rated at 40 volts and 1.5 milliohm RDS on and 120 amps. So if I use this circuit with no added series gate resistance, there's a simulation of turning on the MOSFET. The gate current is limited only by the current gain of the bipolar driver. That's pretty typical of gate driver ICs, where the peak current's limited by internal devices. That peak current's generally shown somewhere on the gate driver data sheet. So here you can see the peak current is about 1.5 amps. The gate voltage, which is the green line, increases from 0 to 12 volts. It's sort of a RC time constant sort of curve. The rise time is limited by the gate capacitance and the drive capability of the bipolar driver. That was that 1.5 amps. You can see a small flat spot in the gate voltage right at the point where the drain voltage is quickly slewing. This flat spot's called the Miller plateau, It's caused by the gate to drain capacitance. That capacitance has to be charged while the drain voltage is increasing. So that charging consumes all the current the gate driver can supply until the drain has reached its final voltage. So that charging process also limits how fast the drain voltage can move. Once the drain's reached its final voltage, the gate drive current then can resume charging the gate to source capacitance, and the gate voltage will continue to increase. With the 1.5 amp peak current capability of this driver, as it's shown, it takes about 200 nanoseconds for the gate to get charged up to the gate supply voltage of 12 volts. But you can see the drain transitions very quickly in about 10 nanoseconds. So here's what turn off looks like with the same driver. Pretty similar to turn on. The gate drive current is the opposite polarity now, as it needs to discharge the gate capacitances. You can still see the flat spot at the gate voltage, which is the Miller plateau, which corresponds to when the drain is transitioning from 0 back to the supply voltage. So quite often you'll see some amount of series resistance inserted between the gate driver and the gate. Why is it there? It's there mostly to slow down the switching speed. We'll talk about why you want to do that in a little bit. So here's the same circuit with a 22 ohm resistor between the driver and the gate. At first glance, this looks pretty similar to the results in the last simulation. But if you look at the time scale, before it took 200 nanoseconds to charge the gate, now with a 22 ohm series resistor, it takes about 1.5 microseconds. The Miller plateau, that flat spot, is much more pronounced. That's because the 22 ohm resistor limits the gate drive current. The peak here is now only 375 milliamps as opposed to 1.5 amps before. It's a little hard to see in this graph, but the drain transitioned in about 120 nanoseconds. That's 10 times longer than it took without that 22 ohm resistor. So you can see it's considerably slower. Here's what turn off looks like with the same driver. Again, it's pretty similar to turn on, but it's in the opposite direction. So what happens if we increase the gate resistor to the extreme, put a big resistor there? So here's what happens, same circuit with 1K, a 1K resistor in the gate. So you can see the peak gate drive current's now only about 10 milliamps, and it takes 70 microseconds or so to charge and discharge the gate. So if you're switching something very slowly, this might be okay. But if you're trying to switch fast, it doesn't work. So here's what happens if we drive a 12 kilohertz square wave, maybe like a PWM signal, using a 1K gate resistor. You can see the gate never gets fully charged or discharged. The drain voltage does still somewhat resemble a square wave, but transitions are really slow. And as we'll see shortly, that means there'll be a lot of power dissipated, a lot of switching loss. So there's another problem with a really weak gate driver, and that's that the gate to drain capacitance can have a big influence on switching and mess things up. If the MOSFET's off, the gate's held at 0 volts but with a high resistance, and the drain voltage moves, maybe by an external source, the gate to drain capacitance can actually cause the gate voltage to increase to the point where the MOSFET turns back on. So this simulation shows what happens when you apply a fast transition to the drain of a MOSFET that has its gate held weakly at 0 volts through a 1K ohm resistor in this example. So you can see when the drain voltage goes up, so does the gate voltage. Gate voltage is in blue here. Goes up to about 8 volts. So I multiplied it times 10 in this graph so you can see it. You would expect with the gate tied to ground that no current would flow through the MOSFET, but actually the gate voltage goes up enough to partly turn the MOSFET on, and about 6 amps of current, this green line, flows through the drain. This unwanted turn-on happens frequently in H-bridge circuits when you're driving a motor or another inductive load that can present a high dV/dt, a fast voltage transition to the drain. When the low side MOSFET turns off, the voltage at the drain rises quickly due to the current flow through the inductance. So that can cause the low side MOSFET to turn back on. Also, the high side turning on and driving the output high can cause the same thing, and that can cause shoot through. Since the high side MOSFET's turning on, the low side MOSFET will turn on and current will flow directly from supply to ground. So to prevent this while still allowing for a slow turn on, a lot of gate driver ICs integrate something called a Millett clamp. That pulls the gate strongly to the source once the MOSFET's fully turned off, even if the resistance is higher during the transition to limit the slew rate. So while we're talking about shoot-through, in some cases, especially when you're driving MOSFETs in a half bridge, you might want the MOSFET to turn on slowly, but off quickly. In a half bridge, that'll help prevent any chance of both the high side and low side turning on at the same time. A common way to do that is to put a diode across a gate resistor. What that does is it lets the resistor limit the turn on time, whereas the diode essentially bypasses that resistor to speed up turn off. So in this graph, you can see that the turn on time is faster than the turn off time is faster than the turn on time. Turn off's about 60 nanoseconds and turn on's about 110. So I've shown you how the gate drive current, or the series resistance in series with the gate, affects the switching time. But, why do you care? So a couple of reasons. Obviously, you need to switch fast enough to pass whatever waveform, like a PWM signal, you want to drive. If the MOSFET switches really slowly, it spends more time in transition from on to off, passing through a region where it's acting like a variable resistor. During that time, it dissipates power. That's switching loss. The amount of power is a function of how fast you switch, as well as the current and voltage that you're switching. So, based on that, you think you really want to switch as fast as possible to avoid switching loss. But fast switching causes other problems. So why do you want to slow the gate down? One reason, there's a lot of parasitic components in a circuit that you don't always think about. On a PC board, traces have inductance and resistance. Wiring to and from the PC board presents more resistance and inductance. Loads often have a lot of distributed capacitance, and power supplies are far from perfect voltage sources. They have impedance. Quite often they can only source and not sink current too. So what's that got to do with MOSFET switching speed? When you switch a MOSFET really fast, there's high dV/dt, the voltage at the drain changes very fast, and the current through the load, dI/dt, changes quickly as well in some cases. So here's an example of what happens when we insert some parasitic inductance in the source lead of the MOSFET. That's kind of typical of a PC board parasitic. So the plot at the left is what we get if we turn this MOSFET off very quickly, and the one to the right shows what happens if we slow it down. They look pretty similar other than the time scale, but look at the red trace. That's the voltage at the source. See how far it goes negative, goes below ground. If it goes too far, it'll turn the MOSFET back on, even if the gate stays at 0 volts. And a lot of gate driver ICs are not happy if you take that terminal negative very far. So another parasitic effect to keep in mind is that the power supplies aren't perfect. They don't have 0 impedance. So when you drive a very fast transition into a load with some parasitic capacitance, and things like motors and solenoids have a lot of parasitic capacitance, then the current drawn instantaneously from the power supply is very large. We usually manage this by adding bulk capacitance to the supply. But the slower you switch, the less bulk capacitance you need to keep from inducing big glitches onto the power supply. Another big problem that comes from switching fast is that it generates EMI, electromagnetic interference. Almost all electronic products need to meet regulatory agency requirements about how much EMI they generate. EMI causes problems with communication systems as the radiated radio frequency energy causes interference. EMI can also interfere with other nearby circuitry just by coupling noise into sensitive nodes. This shows a radiated emissions plot, which is a graph of RF energy versus frequency of a buck converter in this case. The plot at the left shows the EMI when using a rise time of 5.2 nanoseconds, and the one on the right shows the effect if we slow the switching down so that the rise time is 26 nanoseconds. You can see that the RF emissions drop considerably. So another reason to slow down the gate relates to the body diode. So the body diode is a diode that's formed from source to drain that's inherent in the structure of a power MOSFET. It's like any silicon diode. When they're taken from forward current flow into reverse bias, they don't stop conducting immediately. They have a reverse recovery period where current continues to flow in the opposite direction. If the IDT is really fast, the amplitude of the reverse current is quite high, as it takes some amount of time for that diode to recover, and during that time, the current continues to go negative. On the other hand, if the IDT is really low, then the current doesn't have a chance to reach such a high level before the diode recovers. The reverse recovery spike can cause a lot of problems. It often results in a lot of ringing from other parasitics in the circuit, which generates a lot of EMI. And the sharp transient can cause the drain of the MOSFET to go far below a diode drop below ground. That can cause problems in other places, including in the gate driver IC. So that's it for the webinar on driving power MOSFETs. Some things you should remember. It's helpful to understand a bit about how MOSFETs work and how they're made so you can design a successful gate drive circuit. You want to optimize the gate drive circuit to accomplish, whatever your requirements are. Switching speed, slew rate, switching losses, and EMI are all considerations that are sometimes at odds with each other. And you also need to be careful with stray inductances and power supply impedances when you design a board.
Thanks, Pete. Lots of good information today. As it says on your screen, we'll now open it up to questions. There is the Q&A icon on the bottom of your Zoom webinar interface. Just click there and you'll be able to type in questions. I want to remind those who may have joined a little bit late that this presentation will be available. We'll have on-demand streaming of the video as well as the presentation itself. You can go to monolithicpower.com/webinars to see that. So we'll have that up there within a few days. It's also a good spot to go see any of our past webinars. All right, so we do have a couple initial questions. First one I see here is, what simulation tool has been used to generate the charts? Pete?
Well, I guess I'm a little embarrassed to admit this, but it's all in LKeySpice.
Okay. And then the second question was, can you please elaborate on how the MOSFET was falsely turned on?
Sure. Let me go back to that slide. Okay, so in this simulation, we're applying a pulse externally to the drain of a MOSFET that's turned off, okay? So we're holding the gate at 0 volts through a fairly weak resistance, all right? So you would expect this MOSFET would just be turned on. Now the problem is there's significant capacitance from the drain to the gate, right, between these 2 points. So if you apply a signal to the drain, even though the MOSFET's off, that gets coupled through that capacitance down to the gate. So in these waveforms, you can see The red is the drain voltage. In this case, I'm going from 0 to 500 volts. This would be an example of like an offline motor driver or something like that. So it's a big transition. But you can see that couples into the gate, in this case about 8 volts, through that capacitance, because it's that capacitance into 1K resistor to ground. So it jumps up, and that's enough to cause the FET to turn back on.
Okay, next one up, is it possible to destroy a gate with too high of a gate current peak?
That's an interesting question, and I've never really thought about that. I've never heard of it happening. I suppose at some point, yes. There's things like bond wires, inside the device that are limited in how much current they can take. Usually the gate is not a particularly low resistance thing, especially if it's polysilicon. It has some resistance, and I think this parasitic chart show that. If I can find it. Yeah, this RG right here will limit the current ultimately. So I don't know that it's possible to destroy it, because basically it's RG working against those capacitances. So I think RG will probably limit the current to a point where you can't destroy the device, but I'm not 100% sure about that.
Okay. Next up, why is the Miller clamp important, and is CRSS capacitance important for gate driving?
So the Miller clamp is important to avoid this false turn on. So what a gate driver IC with a Miller clamp does is it drives the gate, let's say at turn off, from a voltage down to 0 volts for an N-channel MOSFET with a limited current capability, series resistance, for example. Once it gets it turned off, to prevent false turn on from any activity that might happen on the drain, then you really want to hold the gate down hard, not with a weak resistance. So that's what the Miller clamp does. Once the transition is complete, and some gate drivers ICs will actually look at the drain terminal, so it can tell when it's nearly down to 0 volts for the low side. And then it'll put a hard clamp between gate and source to keep it turned off.
Okay, let's see. I have a DC motor and leg-like mechanism as load, considerable enough, connected to the shaft of the motor. Now when I run the motor by connecting directly to a battery, it attains speed X in 1 rotation. But when the motor is run using a motor driver, it needs 2 to 3 more rotations to attain speed X. I guess this is due to ramp current. Is there any solution to get the desired speed in one go?
So basically that means you have something limiting current. Whether the motor driver IC is doing a PWM ramp to limit the current, or something else is limiting the current, in any case, there's something limiting the current. So the only solution is to remove that current limit. That might not be practical, because if you connect a motor directly to a battery, the initial current, and that's the current that's basically the stall current of the motor, the voltage divided by its resistance, there's really nothing to limit that current. You could be getting hundreds of amps out of a battery for a few milliseconds. Whereas with an IC and a motor driver, you may not be able to get there. So the solution, if it's possible, is to use a bigger motor driver, a higher current limit, and if it's power MOSFETs, really big power MOSFETs.
Thanks, Pete. Next up, what exactly does avalanche breakdown of a MOSFET mean?
So I actually have a slide that I did not show that talks a little bit about that. Let me see if I can find it. So Avalanche, I mean, you can model this different ways, but you can think of it as a Zener diode between source and drain. It's actually not a Zener diode. It's a parasitic bipolar transistor. So what the Avalanche breakdown is if you exceed a voltage between source and drain for some period of time, you will break it down, just like a Zener diode would break down. Some MOSFETs are rated to allow a certain amount of energy in Avalanche. Some MOSFETs are not. The ones that have Avalanche ratings can be used, for example, to drive an inductive load without any kind of a clamp. In that case, you turn the MOSFET off, the inductance makes the drain voltage fly up until it breaks down. You have to be really careful about using that. You do have to make sure that the part can withstand it. And in extreme cases, you will blow up the part, even if it's rated for some amount of Avalanche energy.
What is the calculation of gate resistance?
So I'm not sure if that refers to the actual gate resistance of the device, which is generally, I don't think, shown on a data sheet. And so I don't know where you would get that. Or if he's referring to series resistance into the gate. The series resistance, you can calculate largely based on the amount of time. If we go back to we go back to this, right? You talk about the total gate charge. So to calculate, one way of calculating that resistance is to figure out how much current you need, which you can calculate based on the gate charge and the amount of time you want to slew. So that'll give you a current. And from there, you can start out by just approximating that, you know, the resistor you need is going to be the gate drive voltage divided by that current. So 12 volts, 1 amp peak, 12 ohms, right? Now in reality, you're going to need less than that because gate drive ICs can't source infinite current. So the reality is there's two ways to do it. If you have a good simulation model of your gate drive, you can go with that. What I usually tell people is start with that and test it. You know, put a resistor in, measure rise fall times, and then adjust it from there.
How to calculate diode reverse recovery loss in upper MOSFET from lower body diode of the same leg of the half bridge?
That's a good question. Honestly, I don't know off the top of my head how you would calculate that recovery loss, and I'm not sure exactly what specifications are in a typical MOSFET datasheet. I think they will list a recovery time, but to be honest, I don't know exactly how you would calculate that.
Fair enough. Next, we've got, so with this information, can we say that MOSFETs can be used as a switch for switching between two power sources?
Sure, you can, but you have to be cognizant of the body diode. Quite often when we're using MOSFETs to switch power, you'll see two MOSFETs in series in opposite directions. So one source that maybe you connect the two drains together and the two source terminals are the input and output. And you need to do that because if you just use one MOSFET, when it's turned off, the body diode can conduct current the wrong direction. So quite often you'll see them configured that way. And MOSFETs don't care which direction the current flows once they're turned on. So even though one of the MOSFETs in series appears to be backwards, really it's acting like a diode, essentially.
And next, what's the max speed commercial MOSFETs can switch at?
So there are different types of MOSFETs for different applications. There's MOSFETs designed for RF amplifiers that can run up to maybe a gigahertz or something like that. So for the switching MOSFETs, like we're talking about here, I don't know offhand, but you can certainly get to several megahertz, if not tens of megahertz.
Okay. In many schematics, a resistor is present between the gate and source. 20K ohm, for example, what is that for?
So that's there just to make sure that the gate is always at a known voltage. So one thing you don't want to happen is you don't want to let the gate float. If the gate floats, you'll get false turn on, and you might get partial turn on from leakages as that gate voltage might creep around. So quite often you'll stick a resistor 10 or 20K from gate to source, and that's all that does. If you could think of power up, for example, maybe the power supply turns on and it takes the gate driver a few milliseconds to wake up and actually drive the gate. That's why that's there. You do have to be careful though with high side MOSFETs. A lot of gate driver ICs and bootstrap circuits, for example, can't drive much current. So you do have to be careful not to cause too much leakage on a high side gate.
Okay. Please elaborate on the body diode current path in your simplified model. Also describe use cases of the body diode.
Okay, I believe I have an extra slide here on body diodes. Just a second. So that's the body diode right there. Again, I'm no silicon expert, so hopefully I'm not telling you anything incorrect. But basically, there's a PN junction between the body and the substrate, which is the drain for an N-channel FET. So if the drain goes negative with respect to the source, and you notice the source here, this would be source metallization. It contacts the P body as well as this N-channel area up here, right? So that's where the diode is. You can use the body diode. You can use it, for example, to recirculate current. An H-bridge, maybe you're just turning on, let's say you have one side of the H-bridge set to drive to the supply, and the other one you're just pulse width modulating the low side on and off. When the low side then turns off, the high side body diode takes over and takes the current back to the supply. So you can do that. You have to, just be aware that it's not a great diode. It's not a Schottky diode. It's a silicon diode. But generally, most MOSFETs are capable of taking as much current through the body diode as they are, through the channel.
Are power MOSFET gates nowadays always protected against ESD? Are there Zener diodes or something else built in that limit gate drain voltages to plus or minus 20 volts or whatever the actual limits of the device are?
Good question. They are not all protected. There are some which are, where they actually put a protective Zener there. Most are not. That said, the fact that MOSFETs have a lot of capacitance tends to make them a little less sensitive. It doesn't take much voltage to break it down, but it's a big cap. So it takes a fair amount of current to charge that cap to 20 volts. So bottom line is you still have to be careful.
Okay. When using MOSFETs in parallel to increase current capability, what can we do to prevent one MOSFET with better VGS threshold to take all the current at startup, for instance?
So you could, I mean, you could degenerate it a little bit with series resistance, but typically you don't do anything, because what happens is the guy that turns on first is going to take a lot of current and it's going to heat up. And as it heats up, its resistance goes up. So they inherently share current. So usually you don't have to do anything.
Great. Next, does MPS currently offer MOSFET drivers with an active Millett clamp?
Yes. A number of them have them. I'd have to look to see exactly which ones do and which ones don't. But the ones intended for higher powers, they definitely include a Millett clamp, especially the ones with internal slew rate control.
Great, thank you. How to calculate power loss in a MOSFET?
So there's different components. Usually the dominant one is just current times RDS on, I squared R. That's usually the biggest piece. In addition to that, you need to add in the switching loss, which is a function of switching time and the current and voltage. I think you can sort of envision it, right? I mean, as the current's going up and the voltage is going down, there's a period here where you're dissipating power. It's basically, the voltage and the current, and then multiply that times for example, the slew rate, the turn on or turn off time divided by the PWM frequency. That's basically how you do it.
Okay. How to protect a MOSFET in a half-bridge configuration with drain overshoot?
So that can be a little difficult. You can use transient voltage suppressors, TVSs, for example. You have to be careful because they aren't a very precise breakdown. So you have to have a fair amount of margin in the MOSFET rating as well. In some cases, RC snubbers can be effective to do that as well, to if there's ringing especially.
Okay. What is the calculation and importance of gate to source resistance?
So yeah, I think we sort of answered that before. Calculation, I don't know that anybody bothers to calculate. I mean, to be honest, most people put 10K ohms there. Again, it's only there to keep the gate tied down in the case where the gate driver IC isn't driving the gate. And sometimes that relates to power supply sequencing. For example, if the main supply turns on before the gate driver supply, you do want something there to help keep the gate of that the MOSFET from floating around. But I don't know of any calculation offhand. Obviously, you don't want to burn a bunch of power in it, but usually it's around 10K.
Okay. Next, how do we measure inductance in gate loop?
Boy, that would be hard to measure because the gate loop includes basically everything from the gate driver IC's supply through the gate driver IC to the gate, then across through the capacitance to the source. Maybe you've got a current shunt resistor you got to think about before that current gets back to the gate driver IC. I don't know how you can measure it. You can sort of take a guess at it by looking at PC board, design. I don't know, maybe you can infer what it is based on measuring gate drive current and voltage, but that's pretty hard.
Okay. now we've got, is there any consideration of parameters to select MOSFETs to drive a DC motor other than motor voltage and current?
Generally not. Secondary stuff like package type and that sort of thing. But really, it's about the voltage and current. And the voltage, you need to make sure you have some margin. Depending on the amount of current that's going in the motor, you might need a lot of margin. A lot of customers who are using high currents like 100 amps and battery-powered tools, for example, they actually go for 100% margin. So if it's a 12-volt battery, they'll use at least a 24-volt MOSFET. It depends on the load current. If the load current is low and you have a well-controlled power supply, you don't need that much, but you do want margin. And the current is usually more of an issue about power dissipation. So it's RDS on more than the current of the motor. How much power are you willing to dissipate in the MOSFET? And that relates back to PC board design and heat sinking and stuff like that. So generally, you want a really low RDS on so you don't burn much power. But keep in mind, lower RDS on FET takes more to drive the gate. They have higher gate charge, higher gate capacitance. So that's a trade-off too.
And I think this is a continuation of the prior question that also put in a bleeding resistor.
I'm not sure exactly what that means unless it refers back to the gate discharge that we talked about before, the drain to source, gate to source resistor.
Okay. How to select a MOSFET package?
So it largely depends on PC board design. For most people, smaller is better. To use a surface mount package with limited heat sinking, you need to consider the RDS on and how much heat you can pull out of the device into the PC board. If, a very high current, you either need very low RDS on, or then in some cases, you might use a through-hole package with a heat sink. But it's really all about power dissipation and how and where you want to dissipate the heat.
Okay. And then it looks like our last one is how does the driver IC output impedance affect related power MOSFET driving?
So the driver IC impedance is just in series with any series resistance you have in the gate. So really, when I talked about series resistance in the gate, in reality, that series resistance needs to be added to whatever impedance that the driver IC has. There are cases where some driver ICs are really wimpy and have very high impedance. And in those cases, quite often, you don't add any resistance because the gate driver IC itself is pretty slow. There are other gate driver ICs which have controlled slew rate, which also you don't put any additional resistance, and you rely on the driver changing its output impedance essentially to change the slew rate.
Okay, just when we thought we were getting to the end, Pete, there's more coming in. I see one via chat that was in the waveforms associated with false turn on showing negative voltage on the gate. What was the reference voltage used to measure the gate voltage and the source voltage? Is the spike on the gate voltage the green one because of the negative spike on the source one, red? If source is used as the reference for the gate voltage. Get all that?
Yeah. No, the reference is ground, which is at the bottom of this inductor, okay? So this is the reference for the waveform, 0 volts. The red trace is the voltage on the source, which is above this inductor. That's why it goes negative, right? And what was the other, oh, the green, why does the gate voltage do this? That's an interesting.
And is it because of the negative spike on the source red one? So it kind of inverts there.
I'd have to go back and look at the simulation actually to see exactly why that is. Must be, I don't know what I had in the gate drive here. I'm guessing it's because of some series resistance in this gate. And it's going up because of the gate to drain capacitance. But actually, I'm not 100% sure. I would need to go back and look to see why that was.
Fair enough. Let's see. How to select a MOSFET for a switching application and continue on applications.
I've sort of covered that in various pieces. You know, the voltage rating with margin, the current rating, but primarily RDS on as it relates to power dissipation. And, you know, that also plays into the package and whether it's a surface mount device or a through-hole device. Those are all kind of tied together. Generally, for, you know, drive circuits that are pulse width modulated at relatively low frequencies, like motor drivers, you don't really have to worry much about switching speed.
And then I think this is a follow-up on this slide we're currently on, where the other drawback of fast turn-off is the high VDS spike as shown in the blue waveform. You want to comment on that? It sounds like more of a comment than a question.
Yeah, no, that's true. I mean, it again has to do with imperfect power supplies and bulk capacitance. If everything were perfect, then the drain wouldn't go much above the supply. Well, I shouldn't say that because with an inductive load, obviously it will. In general, whenever you switch fast, there's going to be more overshoot, and quite often ringing with other parasitics. So that's very true. The faster you switch, you will need more margin in the voltage rating of the MOSFET too because of overshoot like that.
Okay, and then we've got, can you discuss MOSFET safe operating area, SOA, and how it influences gate driver selection?
Good question. I'm trying to think of whether SOA really affects the gate drive. I mean, SOA basically only applies during the transition, right? When the MOSFET is switching. But I guess there are SOA considerations having to do with time. So if you can envision switching really, really slowly and you're transitioning through that turn on region before you're turned off, you're dissipating a bunch of power there. And I guess you might run into an SOA issue there. I mean, MOSFET SOAs are fairly forgiving in general. So I have not had to worry about that. It would only become a factor if you're switching quite slowly and you know, at relatively high power levels. It's an interesting question. It may affect your choice on how fast to switch the gate more than anything.
And then we just got another one, another two. How designer, let's see if I get this right. How does a designer think to reduce the output capacitance of the power MOSFET?
So if that's referring to the actual device capacitance, basically it's just a function of the MOSFET. I don't think there's anything you can do externally to alter that, if that's the question anyway.
Okay. And then going back to the prior question, it says, SOA for MOSFET and Body Diode, is it the same as available in Datasheet, I believe is the question?
Should be. Yeah.
Okay. And then MOSFET gate drivers are available in a vast range, like 100 milliamps to a few amps. Is there any disadvantage to use higher current sink source gate drivers?
So the first thing you need to do is figure out how much current you need. And that's a function of the MOSFET, its gate charge or gate capacitance, and how fast you need to switch. From there, that'll give you a minimum. So there's no disadvantage to using a bigger gate driver because you can always slow it down. You can always insert some resistance. The downside is higher current gate drivers are going to cost more money, and quite often they're physically larger. But there's no downside because you can always slow things down. On the other hand, you can't speed them up. If your gate driver can only do 100 milliamps, you're going to be limited with whatever it can do.
Okay. All right, Pete, I don't think they stumped you on too many of those. So, but that looks like our final question. Again, I want to thank everyone for their time, and we'll have the materials out to you within the next few days here.
All right, thanks.
Bye, everyone.